kitty cat who is giving me some gentle bites right here in the form of Suji Mama. Indeed, she likes the lotion that I have put on, and indeed, she is licking and biting me. But welcome one, welcome all, as per usual. Welcome to the live! We are here to discuss black holes and thermodynamics, a topic that we pleasantly started last night towards the end of the live, for which I must thank you for your patience. Thank you for sticking with these live streams. Thank you for sticking with me. Thank you for attending the live streams. Thank you for listening to this video as a video upload later on. If you're seeing this later on, thank you, Heike. Thank you, my old viewers, my old friends and new friends. Hope to see many of you that I know already, and I hope to see many of you that are completely new to me. And I hope that you're sharing these videos with your friends, family, neighbors, cousins, distant cousins, spouses, ex-spouses, and other friends. So, I hope that everybody gathers here tonight for this live stream, and I hope that if not, then you see this later on as a video upload under the live tab on my channel. And we are indeed doing black holes for the 4th night in a row or something like that. I have lost count, because indeed we are reading this book by Stephen Hawking called A Brief History of Time by Stephen Hawking, amazing physicist, of course. And this is the updated and expanded 10th anniversary edition. The book was first published in 1988. In the 10 years since its publication in 1988, Stephen Hawking's book has become a landmark volume in scientific writing with more than 9 million copies sold worldwide. And we're currently on Black Holes Ain't So Black. We've already covered quite a few chapters. It was delightful to read about particle physics, about the expanding universe from the perspective of Stephen Hawking. And of course, then we started the topic of black holes, which he himself has personally contributed a lot to. And so we are very happy to continue that topic. And we kind of finished the chapter, which is called Black Holes. And currently we're on the chapter called Black Holes Ain't So Black, where we discuss the sort of treatment of black holes with thermodynamics considerations. So it's going to be most fun, most amazing, most exciting, and I hope that many of you will be joining me very, very soon. And if you're coming, if you're here, say hi in the chat, say hi, send a chat message. Hello, Fire Night TV. Hello, Claudia. Hello. Once I see your chat messages, I will read out your comments. I always spend some time towards the beginning reading every comment, reading all your usernames, and giving a shout out. So thank you so much for being here. So let's see. We have Fire Night TV. Thank you for liking the live. Thank you for the hearts. Thank you for the tap emojis, and thank you for double tapping the screen that will tell me that you're here and liking the live. Thank you so much. Can we get 20 likes? Can we? Fire Night TV. Hello, Claudia. Hello, Jesus Zavala. Hello, Zabibullah. Ergash Zohayev. Hello, Jesus again. Hello, Havik. Hello, JG2 Goated. Hello. Thank you so much for being here. I'm trying to read this name. Vani of Aravani. How are you? Says that name, very pretty. Hello, Jesus again. Hello, Saeed. Hello, Saeed Muni. Where are you from? Hello, Zabibullah. Hello, Fire Night TV. Hello, Havik again. Hello, Saeed again. Hello, Henry Rice. ASL, American Sign Language. I don't know too much about that. Ashwani. Oh, I'm so sorry. I see. There's the S and the V together. The V together with the S. I'm so sorry. My eyesight is a little hazy right now, actually, because I was just swimming. And sometimes I don't see so well after I have just been swimming. So, Ashwani, thank you so much for being here. I'm trying to read the last name as well. Is it Miksha? I'd really like to read it. Mimi and Nini says, hi, I'm from India. Hello, Mimi and Nini. Saeed Muni says hi. Annie says hi. Where are you from? I am originally also from India, but currently I'm in Boston in North America. Fahrenheit TV says one day you will become better than Mr. Beast. Oh my gosh! Thank you, thank you, thank you. Welcome to the live. Welcome one, welcome all. Thank you so very much for being here and for your encouragement. JG2 Goated says, do you talk about cosmic objects? Yes, so tonight we're talking about black holes generally. But yes, I generally talk about physics, astronomy, astrophysics, and cosmology. Along with kitty cats, I have some children who are kitty cats, as you can see. They also appear on the videos. It's basically a cats plus physics channel. So here we are. Here's one of my kids. This is my daughter, Suji Mama. Steven Spears. Hello. Hi all. Says Steven, sneaking in and raps on all the shoulder. It's Queen. Hi. Hello, Queen. Hello, Ashwani. JG2 Goated says, Ward, I'm tuned in. Thank you, thank you, thank you, thank you, thank you, thank you. Thank you for being here. El Challen, ciao, ciao, ciao. Hello, El Challen. How are you? Let me make sure that I got everybody. I think I've said everybody's name here. Fahrenheit TV said, nice science. Thank you so much. What is a white hole? Somebody asked. I'm not sure. If I have an answer right now for that. How are you? Had asked Ashwani. I'm good. How are you? Thank you for the hearts. Zabibullah. One day you will be a millionaire, says Fahrenheit TV. Thank you so much. Same to you. Explain what a white hole is. I am from India. I'm just making sure I got everybody's messages and saw the questions if there was any. And I love this comment. One day you will become better than Mr. Beast. Goodness. Thank you, thank you, thank you. It's Queen says, I'm from Indonesia. Oh, wow. My neck just did a whole thing. Okay, yeah, it cracked a little bit. Okay, because I was in a weird position, I think my neck was like complaining a little bit. It's Queen. Hello, Indonesia. Welcome, Indonesia. You from? So I'm in Boston in North America. I'm originally from India, so not a very far neighbor from you, Indonesia. I'm in the United States, in Virginia, says Stephen. Welcome, Stephen. Welcome, Virginia. Welcome, Boston. Welcome, Belgium. Welcome, UK. Welcome, United States. Welcome, Indonesia. Welcome, India. Welcome, Pakistan. Welcome, Asia, Africa, Europe, North America, South America, Antarctica, Australia, New Zealand. I hope I covered everything. I once saw a blue-white light fall from the sky, hovered 3 to 5 seconds, 3 feet off the ground, and went up to the sky. Hello, El Challen. Lovely to see everybody. How is everyone doing? How is everyone doing? Lovely to see everybody and to read all your messages. We will start the topic of the day very soon. So if anybody wants to come in and say hi now is the time. Otherwise, I'll catch you in between my readings and in between the discussions. But lovely to see so many chat messages. Thank you. Thank you, everybody. Can we get 20 likes? Somebody, one of my mods, please do come in and... hello, all, says Steven. Please do come in and say that thing. We need 20 likes, and then I will pin it. Oh, and of course, I should share the live on my channel. 1 second. Let me share the live. Let's see. Let's see. I feel like I use this phone mainly to share my live and do things while I'm using my main phone to do the... Yay, thank you, El Challen. El Challen says we need 20 likes. I pinned that. Thank you so much. Steven, hello. Steven also said we need 20 likes. Thank you, Steven. Steven says I already liked. Thank you. El Challen, thank you. It's Queen, thank you. Can you speak Indonesian? I cannot. You should teach me a few words in Indonesian, though, in the chat if you'd like. Thank you. Welcome, it's Queen. Welcome, El Challen. Welcome, Steven. Welcome, everybody else. Thank you for being here. Stephen, are you excited about black holes and thermodynamics? We're about to launch into Hawking radiation, I think. I think we're in that spot in the book. Are you excited? Let me share the live and say that. Say hi to everybody and say hi in the chat. Yay! Okay. I will say to my channel, we are live. Where is everybody? In fact, I will tag a few people. Fuji, I'm over here. Fuji. So my mom is visiting, and Fuji is. Hi, Fuji. I'm over here. Are you confused where who is? Are you confused? Mama's here, Fuji. I barely speak English. Yes, I am. There's a movie I will always speak of called The Black Hole. Hello, Steven. A fan of the Beverly Hills OFC says Hook. Hi. Hi, a fan of Beverly. Its queen says, I have some business, I'll go first. Okay. See you next time, it's Queen. Please do like, share, and subscribe. Please do subscribe. Would love to see you back here on my lives. Hello, Fuji. Thank you for coming back to my live, Fuji. He had gone off to explore a little bit. So I am telling the channel that we are live. Sorry that took a minute because I was trying to tag some people, my mods and such. So, Stephen, why are you saying that you barely speak English? Yes, I am. There is a movie. Okay. Oh, I see. You're saying that you're excited for Hawking radiation. Got it. Thank you, it's Queen. Chickpea, hello. Hello, Ver. How are you? Just playing with their minds. Oh my gosh. Chickpea, today I had a very big lunch/dinner. I ate some Nepali food today, so I'm quite full. I ate a Nepali thali with mutton. Chickpea says I'm okay. Aw, Chickpea, what have you been up to? We didn't see you for a little bit. What you been up to? Thali with mutton, yeah. I ate a Nepali thali with mutton with my mother. She's visiting. And both of us don't really like cooking. Actual food. Today, well, chickpeas are actual food. What do you mean? Today I ate some actual food. Isn't that amazing? It was so exciting. When I saw that thali come out, it's like happiness. That is my happy place. That and a couple other things like the ocean, pretty much my happy place. I've been working so hard that you can't even come to the live. Goodness. I had Irish stew recently for St. Patrick's Day. Good job, Stephen. I had a bit of a corned beef hash, something. I had part of an Irish meal. I ate off of somebody's meal. Actually, I've been sleeping hard after work. You've been working hard and sleeping even harder. I got you. I gotcha. I see. Sleep is important. I see. I understand the struggles here. I do. Okay, everybody, thank you so much for being here. Please do like the live. Welcome, welcome, welcome. Can we get 20 likes? Sleep is overrated. I kind of wish that we didn't have to sleep all the time. As in every day. I kind of wish that we didn't have to eat and sleep every day. Hi, baby. Fuji's over there looking at me expectantly. Hi, I know that grandma has fed you. I went to the gym and their grandma fed them their dinner. Gosh, I'm still thinking about my dinner. Look at sleep like meditation. Wow. Anyways, thank you guys, everybody, for being here. Let me get this show started. So we were at the black holes and thermodynamics portion of our chat last night. So we're on the chapter currently called Black Holes Ain't So Black. So Stephen Hawking introduced the topic of black holes. Of course, it's a type of stellar remnant. It can start as a star that dies, and we saw how it was predicted to be a sort of object on a type of singularity. That happens from a massive star sort of collapsing on itself under its own gravitation once it runs out of nuclear fuel. But people didn't really fully believe that black holes could be real because it just seemed so bizarre of an object. And this point of infinite density, this whole thing, the singularity thing was a little bit difficult to believe, even though it was predicted by general theory of relativity. But some of the theorists who sort of rooted for it, he talked about in the last chapter, they were very encouraged, very enthused when they saw the first evidences of neutron stars, because neutron stars were very compact objects. They were coming, also another type of stellar remnant coming from massive stars. And those massive stars, when collapsing under their own gravitation, collapsed to and compressed to something as small as a 10-mile radius in the case of neutron stars. So once people saw that, they were like, oh, holy moly, stars really do collapse to extremely compact objects sometimes. There's a kitty cat fight about to start here. Fuji, come Fuji. Come baby. Don't hit Baji. Be a good boy. Mama loves you. Mama loves you. Mama loves you. I have to pacify him so that he doesn't attack my other son. So I know how to meditate. I had a So we saw how the three types of stellar remnants were kind of discussed. The first type is white dwarfs. So those are good. Those are for stellar masses under the Chandrasekhar limit. So not too heavy mass stars can basically, when they die, kind of collapse into a white dwarf. Even heavier stars, quite a bit heavier stars, more massive stars, when they collapse into neutron stars. And the heaviest stars, when they collapse, can collapse into black holes. But at first, even though black hole as a mathematical object was around and known about and, I guess theorized about and calculated for, but people didn't quite believe that such a thing could exist. But they got a lot of enthusiasm. Some of these people, the black hole theorists, got a lot more enthusiasm when neutron stars were seen for the first time, because they were like, oh, whoa, stars can collapse to something as small as a 10-mile radius object, which is what a neutron star is. So even more compact than white dwarfs. So that is sort of the part of the kind of trajectory for the discovery of black holes. And then, of course, people started to see actual real black holes in the wild as well in nature. So now we know, we have observations for black holes. We kind of see that sometimes a very large black hole, like a supermassive black hole, sort of like the one that's at the center of our own galaxy, Sagittarius A star, can sometimes actually get very big by eating more and more material and making the material around the black hole or nearby objects or even stars around the black hole to kind of accelerate towards the black hole and fall into the black hole. And in the process of that acceleration, those things, those falling infalling material can actually produce a lot of radiation, and those types of radiation can actually give the black hole away. So even though a black hole is quite dark and even light cannot escape it, it can kind of give itself away with all of the eating that it might do, especially in the case of a supermassive black hole. But now we're going to see what else black holes do that may be sort of interesting, or not what may come to mind immediately when one thinks of black holes. But indeed, the basic things to keep in mind is that it's a type of a stellar remnant stars. So if you're ever studying stars and their evolution, their life cycle, you will see that stellar remnants come up, as in what does a star become upon its death, upon its collapse onto itself, once it runs out of nuclear power. Because the two big things going on in a star, of course, one is the nuclear reactor and its belly, keeping it alive, keeping it going, keeping it burning, and then its own gravitation, because stars are massive, very massive objects. So once it runs out of nuclear power, there's sort of nothing to keep it as a star, and it will collapse under its own mass or gravitation. So once that happens, there is basically like three possibilities for a star to become a type of stellar remnant upon its death. And these are white dwarf, neutron stars, and black holes. So we're on the topic of black holes. We will keep learning more about what Stephen Hawking has to say about black holes. The part that we're currently on is sort of about black holes being something that can still emit some sort of energy, maybe some sort of like black body E type of radiation. And we will see how he found that. So let's see. Hi, Athula. Thank you for subscribing. Athula says, I subscribe. Good morning. Thank you. Neutron stars are pulsars. Yes. So exactly, we talked about the pulsars and how they were discovered, and gave black hole theorists hope about maybe they weren't so crazy to think about something like a black hole upon finding that there were things called neutron stars. I want a dying star as a souvenir. So yeah, the pulsar having a very strong magnetic field is basically the something that gives pulsars their property. I watched a video some years ago where they showed stars orbiting around a black hole, Sagittarius A star. So Sagittarius A star is the supermassive black hole at the center of our own galaxy. Combat Sports, hello. It pulses like a lighthouse, hence the nickname Lighthouse of the Universe. Yes, exactly. So there is some directionality associated with the radiation, and generally because they are also spinning, rotating, they have quite a bit of angular momentum. So because we see the directional radiation coming off of such a neutron star every so often, basically there's a period associated with this radiation. That's why they're called pulsars, lighthouses, things like that. So somebody asked, JG2 Goated asked, and once they stop giving off that radiation, it devolves into a neutron star. So a neutron star can be a pulsar, basically. So a neutron star is sort of a, not the best name, because the star is part of the name neutron star, but a neutron star is not really a star. It's a compact object, which is really a stellar remnant. So a neutron star, in other words, is a dead star. So it used to be a star which had a nuclear reactor in its belly, went through its evolution, stopped doing nuclear reactions at some point after running out of its nuclear fuel, and then goes through some supernova process, and then eventually compresses down to something which is a compact object with a very small radius of the order of 10 miles. And it's supported by neutron degeneracy pressure. And that is what we call that remnant, or the dead star at the end, is what we call a neutron star. Okay, so it's not really a star. Neutron star together is it's the name of it's a type of stellar remnant. So when we talked about stellar remnants in one of our lives, we've talked about it in a few different lives, but we've talked about the types of stellar remnants. Stellar remnant meaning it's not a star anymore, it's died, basically a dead star. So dead star type number 1 is white dwarf. Dead star type number 2 is neutron star, where the word has the star in it. The name has the star word in it, but it's not really a star anymore. And then dead star type number 3 is black hole. So black hole is a type of dead star. And then black holes sometimes can continue to eat a lot more material over the course of time, just like our own black hole at the center of our own galaxy has done. And that's how it becomes a more massive black hole, or a supermassive black hole. Eventually, it probably didn't start off with that mass. It's eaten a lot more matter over the course of its lifetime as a black hole. So because once a star dies and becomes a black hole, now we're talking about the black hole. It's a dead star. It's going to do black hole things. You know what I mean? We don't consider it a star anymore. Okay. But that's a great question also. When two neutron stars collides, what happens? So that's a great question. That's a great question. So neutron star merger is what you're asking about, right? You could maybe make a black hole at the end of that. You might. So basically, one thing for sure that's going to happen is you could have basically a binary system of two neutron stars that are basically companions. They're orbiting each other, etc. And if you saw my live on gamma ray bursts, actually, gamma ray burst is a transient event in the sky that can happen, and they're very luminous events. They're the most luminous events basically when they do occur for the brief period of time when they are occurring. So something like a neutron star merger would first of all, it would release gamma rays. So basically there would be a cataclysmic explosive event, and we would probably get gamma rays, short gamma ray bursts actually from such an event. It might collapse into a black hole. We would probably get gravitational waves from that. So gravitational wave observatories started to see gravitational waves from events like exactly the one you ask about. So basically these types of systems where there is a binary of neutron stars, or a binary of two objects, it could be a black hole and a neutron star, or a neutron star, or a black hole, you know, once they do merge, because the whole time actually such a system will lose gravitational energy as they're orbiting around each other, as they're doing the little dance around each other. They do lose gravitational energy, so the gap between them is actually getting smaller and smaller. So you're right that eventually they would probably merge, and once that merge happens, well, for sure there's going to be a cataclysmic event, and actually such a merger is the source of short gamma ray bursts. So we would see such a thing hopefully in a multi-messenger astronomy kind of way. So we could see gamma ray bursts from that. So as in gamma rays, so photon type of signature of such an event. We could see gravitational waves from such an event, especially if we're sensitive. Sometimes on Earth, we are only sensitive to extremely bigger such events like some big merger. The first ones that we started to see with the, for example, with the LIGO experiment were some really big ones. But if we become more and more sensitive, or if we put gravitational observatories in space, we might even pick up on sort of lesser events, not as big things merging, but maybe even smaller things merging. So, it would be sort of this big event in the sky that we could get gravitational waves from, gamma rays from, maybe neutrinos from, and all kinds of things. So it would be quite an interesting phenomenon, and it may result in a black hole. That could happen, yes. I need a way to harvest dark matter and figure out a way to use it for the benefit of mankind. I was a little confused on that. Yeah. Okay, yeah, good. That's good. Hopefully that helps. Hello, the Bears. Hello, JG. Hello, Chickpea. Hello, Steven. So, yeah, I don't know where Doro is. Great questions, JG2 Goated. No, this is perfect. Any more questions, just let me know. This is perfect. I'm liking it too. Basically, these are relevant to the topic anyway, so I'm happy to address your questions. And I'm glad that you asked about the confusing naming. For sure, some of the naming in astronomy can be a little confusing. And neutron stars are not really stars. They are dead stars. So, yes, thank you for clarifying. So, great questions indeed. Very, very good questions today so far. This question about the neutron star merging, or a neutron star and a black hole merging, or a black hole and a black hole merging, these types of events are very much studied in astronomy, in astrophysics. So what you're asking about is something, it's a very relevant topic. It's an area of research. And those are, interestingly enough, those are the events that we're trying to learn more about and use to kind of get gravitational waves. So the first measurements of gravitational waves were from such events. So these are actually very, very important events as we're trying to gain more and more expertise in doing multi-messenger astronomy, understanding astronomy with not just one type of signature, but with multiple. So it could be photons, it could be other particles like neutrinos or cosmic rays, and it could be gravitational waves. So that's called multi-messenger astronomy, where from the same event, you might be able to probe it with multiple things. It could be photons that you get from that event. It could be neutrinos that you get from the event. It could be gravitational waves that you get from the event. And when you do it this way, when you do multi-messenger astronomy, then you're able to probe an event further. It's not just the gamma rays that I'm getting from such an event, or just the gravitational waves. Because actually, another big thing about LIGO, and when they first measured yes, I believe when they first measured the gravitational waves from the neutron star merger, if I'm not mistaken, that was the first confirmation of gamma ray bursts with neutron star merger. So we actually theorized that short gamma ray bursts come from neutron star, or neutron star black hole, or black hole mergers. So binary systems which have these companion objects, when they continually rotate around each other, orbit each other, and eventually when they merge, we thought that short gamma ray bursts, which is a type of transient event that we had been that we had seen, but we didn't know exactly what caused them. We had thought about that, but it was confirmed when we measured both the gamma rays as well as the gravitational waves from such an event, from such a merger. So these mergers that you're asking about are extremely interesting to everybody. So keep asking your questions. I think those are basically the areas of research at this time. I wonder if a black hole can somehow be contained according to its size. So Okay, so did I tell you guys? I think I did tell you guys that anything actually can be a black hole. So to be a black hole, you just need to be compressed enough. So even you can be a black hole, chickpea break. There is a Schwarzschild radius. Basically, Einstein's general theory of relativity equations were solved for the first time exactly for a black hole by Schwarzschild. And basically, for the equation of a black hole, you just have mass and radius as being obviously very important things in that equation. And depending on your mass, if you're compressed to a small enough radius, then even you could be a black hole. So actually, it's not just about being a very massive body, it's also about the compression. It's about that infinite density. It's about being that singularity in space and time, which makes a black hole a black hole. So people had mathematized, if that's even a word, people had basically done the mathematics for, oh, can something be compressed so much where you basically compress something down to a singularity, and then they call it a black hole or a point star or a dark star without actually knowing that black holes are real and they're actually things in nature and in the wild. So people thought it's too crazy. A lot of people, even Einstein, probably thought that it was too crazy to find, like, to actually have black holes in nature, you know, just like the cosmological constant, which turns out to be dark energy or even dark matter. These are areas of research that we still don't understand exactly what dark matter is, what dark energy is. But what black holes are, we do get it. We actually see them in nature. They're actually a thing. So that is one crazy thing that actually came true. It wasn't just a math object. It wasn't just an equation that they solved and this infinite density thing was not real. No, it was actually real. So because they were like, okay, well, you know, stars, when they die, they collapse. So could they collapse so much to the point of a compression where it would be that infinite density, it would be that singularity, which is basically the black hole. But so how about finding a way to expand the compression? So expanding the compression would be to basically have the star be alive. Once the star has died, it's difficult. Actually, that's not completely true. It depends. In the case of a nova, which we can read about, actually somebody asked about the nova yesterday. In most cases, okay, let me just say this. In most cases, if a star has died, you can't easily rekindle it to be a star again. So it's going to be hard to go from a cold, dead star to an alive star again. There is a process that I want to talk to you about, which is the nova. And somebody asked about that yesterday. So that's funny that you kind of bring this up. So I do want to talk about that particular process. But generally, in most, I would say in most cases, when the star has died already, so Wonder Boy is Reese, but yeah. How is Hawking radiation possible if black holes are so infinitely dense that photons can't escape it? That's a great question. We're going to read about that right here, right now. Stephen Hawking's research is on that. So he will be telling us about this with his book. But that's a great question. Hawking radiation, absolutely. Hello, Reese. Hello, Chickpea. Hello, JG. So, but yeah, anyway, hopefully that helps. Basically, it's hard for you and me to be compressed so much where we become a black hole. But because stars are so massive and when they collapse, they do get compressed a lot because of their death and because of the nuclear power running out, that it is actually kind of plausible that they could get collapsed and compressed enough to make a black hole. And that's exactly what people predicted, the black hole theorists. And that is exactly what we actually see in nature sometimes. And that's how we get black holes to begin with. But the uncompressing thing that you're asking about, that would be to say that a star, it's dead, it's made a black hole. Can you now rekindle it? I don't know about rekindling a black hole. I think that would be hard, but we can talk about how sometimes some things may happen with white dwarfs that lead to certain more energetic situations in the form of a nova. So we can talk about that in a bit, or maybe another day, because today I want to continue with the black holes. But great question though. I'm going to keep it in mind to talk about nova again. Somebody had asked about that anyways in the previous live. Okay, so as you might know, the second law of thermodynamics basically talks about entropy and how entropy always increases. So this is something of importance in this particular discussion that we're having today about the black holes and how thermodynamics may play a role with this insight with the black holes. So this whole concept of the black holes, basically things are going in, nothing is coming out, would kind of lead one to believe that you're losing the information in some way. But is that really the case? That's what is being probed here by Stephen Hawking and others. So let's read here. The second law of thermodynamics has a rather different status than that of other laws of science. So by the way, the second law of thermodynamics, which is that entropy always increases, entropy in a system always increases, is by the way, a lot of people's favorite law. But it's not the same exact kind of law as some of these, some other laws that we may talk about, like Newtonian laws. So let's see. So it's not quite the same as some other laws of science, such as Newton's law of gravity, for example, because it does not hold always, just in the vast majority of cases. So it is a lot of people's favorite law, but it only holds in the vast majority of cases, not necessarily always. The probability of all the gas molecules in our first box. So we had talked about a box and having gas molecules in it and what sort of configuration of these configuration those would take in the box. The probability of all the gas molecules in our first box being found in one half of the box at a later time is many millions of millions to one, but it can happen. So basically, we're saying that entropy of a system generally increases. So if the gas molecules all sort of arranged themselves very perfectly to one corner or something like that, that would be quite improbable, but I suppose it could happen. It's a very small chance, but it could happen. Just in the vast majority of cases, probably not. So that's what he means here. However, if one has a black hole around, there seems to be a rather easier way of violating the second law. So violating the second law in the case of the gas molecules by saying that, oh, maybe the gas molecules, there is a little chance, very small though, that the gas molecules will arrange themselves in a very tidy manner. The chance is very small, but it could happen. But what about with a black hole? Once there is a black hole, it seems like we're sort of maybe violating this second law. Just throw some matter with a lot of entropy, such as a box of gas, down the black hole. The total entropy of matter outside the black hole would go down. One could, of course, still say that the total entropy, including the entropy inside the black hole, has not gone down. But since there is no way to look inside the black hole, we cannot see how much entropy the matter inside it has. So it is basically sort of to the point of asking, to the point of somebody, when somebody asked about, it's only eating things, it's only kind of swallowing things in, but what about something coming out, such as the information about the entropy that we just did something about, right? If we just throw a bunch of gas, like a box of gases into the black hole, and it swallows it, we now don't really have information about what happens with the entropy. Is it true that now that information is lost forever? Is it sort of a violation of the second law of thermodynamics? What is up with that, one might ask. So, so one could say that the total entropy has not gone down. But since there is no way to look inside the black hole, we cannot see how much entropy the matter inside it has. It would be nice then if there was some feature of the black hole by which observers outside the black hole could tell its entropy, and which would increase whenever matter carrying entropy fell into the black hole. So they're asking, is there some way of knowing from the outside of the black hole that something has happened, that some entropy carrying matter has fallen into the black hole? Now we understand that we won't be able to look into the black hole, but is there anything at all that changes or does something on the outside which would tell us that the entropy or that it has done something, that some entropy increasing thing has been swallowed whole, or some box of gases has fallen in, something, anything? Give us a clue, nature, is what we're asking here. So what is that thing? Is there such a thing, and what is it? So again, it would be nice then if there was some feature of the black hole by which observers outside the black hole could tell its entropy, and which would increase whenever matter carrying entropy fell into the black hole. Following the discovery described above that the area of the event horizon increased whenever matter fell into a black hole, so they actually found that the area of the event horizon increased whenever matter fell into the black hole. So there is a clue that is given by nature on the outside, where you don't have to die to find this out, which is that the area of the event horizon might be increasing. So this discovery was made. A research student at Princeton named Jacob Bekenstein suggested that the area of the event horizon was a measure of the entropy of the black hole. So we talked about this a little bit yesterday, that somebody called Jacob Bekenstein, so not Einstein, but Bekenstein, found that the area of the event horizon might be increasing when the black hole swallows something with more entropy. As matter carrying entropy fell into a black hole, the area of its event horizon would go up, so that the sum of the entropy of matter outside black holes and the area of the horizons would never go down. Yeah, we can talk about a wormhole. Yes, maybe in a bit. We certainly can. This suggestion seemed to prevent the second law of thermodynamics from being violated in most cases. However, there was one fatal flaw. If a black hole has entropy, then it ought also to have a temperature. So now that we're in the sort of domain of thermodynamics, like we're literally talking about entropy of a black hole and how it swallowed matter or entropy carrying matter and did something, which is that it increased its event horizon size or area or whatever. Well, if we're talking entropy, well, this person at Princeton worked on it and suggested sort of an entropy associated with black holes. That suggestion itself actually carries this deeper meaning that if something has entropy, if we're doing thermodynamics, then we also ought to have a temperature associated with the black hole. And therein lies the main meat of the topic here, the radiation. If a black hole has entropy, then it ought also to have a temperature. But a body with a particular temperature must emit radiation at a certain rate. This is black body radiation. We know that if something has a temperature, you, me, everything, anything with a temperature is gonna radiate some kind of thermal radiation, some black body radiation. If we're suggesting that a black hole has a temperature, then it must radiate something. And what is that radiation? It is a matter of common experience that if one heats up a poker in a fire, it glows red hot and emits radiation. But bodies at lower temperatures emit radiation too. So we know that hot things, really hot things that we are familiar with, will emit some kind of radiation. That's how we get heat. That's how, everything, basically this thermal radiation is very common. But generally, we don't think of radiation coming from lower temperature bodies, but pretty much anything with a temperature is going to have some radiation. It might just be very small. So one just does not normally notice it because the amount is fairly small. This radiation is required in order to prevent violation of the second law. So black holes ought to emit radiation, is what Stephen Hawking thought. But by their very definition, black holes are objects that are not supposed to emit anything. They're not supposed to emit anything. We did the math. Remember, all the mathematics and the mass and the radius and the black hole requirement of something was done keeping in mind that the escape velocity from a black hole is the speed of light. So basically, even light can't escape. The event horizon is where even light rays are struggling to escape, and you just get darker and darker. We showed a diagram of a black hole last night towards the end of the live. So the mathematics is set up to have the escape velocity be the speed of light. But here we are with maybe some kind of temperature associated with a black hole, and it's as a research topic. Stephen Hawking is thinking about working on it here as he's talking through it here, because people hadn't really pieced this together yet, which is that a black hole, the entropy, temperature, meaning radiation. That whole piece was not pieced together yet. But by their very definition, black holes are objects that are not supposed to emit anything. It therefore seemed that the area of the event horizon of a black hole could not be regarded as its entropy. In 1972, I wrote a paper with Brandon Carter and an American colleague, Jim Bardeen. So Stephen Hawking is saying that he wrote a paper in 1972 with Brandon Carter and an American colleague, Jim Bardeen, in which we pointed out that although there were many similarities between entropy and the area of the event horizon, there was this apparently fatal difficulty. I must admit that in writing this paper, I was motivated partly by irritation with Birkenstein, who I felt had misused my discovery of the increase of the area of the event horizon. Oh my gosh. Some drama between physicists. However, it turned out in the end that he was basically correct, though in a manner he had certainly not expected. So he was irritated because of some misuse of the discovery of the increase of the area of the event horizon. I guess all the black hole theorists might be a little bit up in arms with each other, but in the end, Birkenstein was correct in a manner that he had not expected. We will find out. In September 1973, while I was visiting Moscow, I discussed black holes with two leading Soviet experts, Yakov Zeldovich and Alexander Starobinsky. They convinced me that according to the quantum mechanical uncertainty principle, rotating black holes should create and emit particles. So this is where he kind of brings in some quantum mechanics to the picture, something that was kind of missing so far, because the whole light escape velocity, the speed of light escape velocity, the general relativity equation solving to get the black hole and the mass radius, all that, that's sort of the classic approach. That is sort of the classical approach. That is sort of the relativity approach. But remember, there was another whole thing going on in the 20th century called quantum mechanics, which also had some bizarre implications. Maybe it was time to give the black hole some quantum mechanical treatment. So let's see how that went. I believed their arguments on physical grounds, but I did not like the mathematical way in which they calculated the emission. So these two people from Russia, they were basically saying that quantum mechanically, a black hole should probably create and emit particles, especially the rotating black hole. But Stephen Hawking was not super sure yet, especially with the mathematics of what they had done. I therefore set about devising a better mathematical treatment, which I described at an informal seminar in Oxford at the end of November 1973. At that time, I had not done the calculations to find out how much would actually be emitted. I was expecting to discover just the radiation that Zeldovich and Starobinsky had predicted from rotating black holes. So he'd already kind of looked at what Zeldovich and Starobinsky had predicted for the rotating black holes, and seeing, maybe he's thinking that what he finds will be sort of a discovery of that radiation that they thought of. However, when I did the calculation, I found to my surprise and annoyance that even non-rotating black holes should apparently create and emit particles at a steady rate. At first, I thought that this emission indicated that one of the approximations I had used was not valid. I was afraid that if Bekenstein found out about it, he would use it as a further argument to support his ideas about the entropy of black holes. So he's kind of worried about Bekenstein here, which I still did not like. So he still didn't like the entropy argument and how Bekenstein had done something with the event horizon increasing, whatever. However, the more I thought about it, the more it seemed that the approximations really ought to hold. So he's finding with his work that the black holes are emitting something at a sort of steady rate and emitting more than he would have expected. But it's not because something he's done is wrong. He may be a twat. Who knows? He might have been. I think is at this time dead. But what finally convinced me that the emission was real was that the spectrum of the emitted particles was exactly that which would be emitted by a hot body, and that the black hole was emitting particles at exactly the correct rate to prevent violations of the second law. So it would be one thing if his emissions were a lot and also did not follow any physically known thing, but it kind of followed the emission that was from the spectrum of the emitted. It kind of followed the spectrum of emitted particles from a hot body, or sorry, from emission from a hot body. So it kind of made sense, basically. So, and that the black hole was emitting particles at exactly the correct rate to prevent violations of the second law. Since then, the calculations have been repeated in a number of different forms by other people. So on the list of what? Since then, the calculations have been repeated in a number of different forms by other people. They all confirm that a black hole ought to emit particles and radiation as if it were a hot body with a temperature that depends only on the black hole's mass. The higher the mass, the lower the temperature. Wow. How very interesting. This is yet another, oh my gosh. This is yet another instance. This is yet another instance where something in astrophysics, something important, depends on the mass of the star, and in this case, the black hole. So, turns out, the higher the mass, the lower the temperature. How is it possible that a black hole appears to emit particles when we know that nothing can escape from within its event horizon? The answer, quantum theory tells us, is that the particles do not come from within the black hole, but from the empty space just outside the black hole's event horizon. Goodness. This is quite dramatic. Okay, so once again, how is it possible he went to the island? I don't know, man. I haven't been to that island. So, could have. I don't know. How is it possible that a black hole appears to emit particles when we know that nothing can escape from within its event horizon? The answer, quantum theory tells us, is that the particles do not come from within the black hole, but from the empty space just outside the black hole's event horizon. I actually don't know much about the island. Go ahead and describe it, I suppose, as harmlessly as you can. We can understand this in the following way. What we think of as an empty space cannot be completely empty, because that would mean that all the fields, such as the gravitational and electromagnetic fields, would have to be exactly zero. However, the value of a field and its rate of change with time are like the position and velocity of a particle. The uncertainty principle. Oh my gosh, remember? We talked about the uncertainty principle and how that's a thing in quantum mechanics. It comes back here. So the uncertainty principle implies that the more accurately one knows one of these quantities, the less accurately one can know the other. So position and velocity of a particle, just like we cannot know both in quantum mechanics, same thing. The value of a field and its rate of change with time are like the position and velocity of a particle. When you know one, you can't really know the other. The limit, there is an uncertainty limit on it. So in empty space, the field cannot be fixed at exactly zero. It's not always exactly zero, because then it would have both a precise value 0 and a precise rate of change also 0. So because you can't really know the field and its rate of change at the same time, uncertainty principle tells you that you can't. Basically, you can theorize that there's still something happening there. Maybe there's a probability. There must be a certain minimum amount of uncertainty. So the uncertainty principle is giving you sort of an uncertainty limit really on a certain measurement, right? So it's like having errors on something. You can't just say both of these things are 0. There is some uncertainty with that answer. And within that uncertainty, you can have something else happen, something different happen, right? So there must be a certain minimum amount of uncertainty or quantum fluctuations in the value of the field. One can think of these fluctuations as pairs of particles of light or gravity that appear together at some time, move apart, and then come together again and annihilate each other. So there could be these quantum fluctuations happening in that space where the field and its rate of change cannot be both known at the same time because of the uncertainty principle. Basically, the uncertainty principle is kind of giving you permission to just suggest something you'd like to, in this case, Stephen Hawking. So one can think of these fluctuations. So there could be some quantum fluctuations because of the uncertainty principle, and one can think of these fluctuations as pairs of particles of light or gravity that appear together at some time, move apart, and then come together again and annihilate each other. These particles are virtual particles, like the particles that carry the gravitational force of the sun. Unlike real particles, they cannot be observed directly with a particle detector. So we talked about how virtual particles are a thing in particle physics. When forces are carried and interactions happen between two matter particles, sometimes some of that is considered to be a virtual particle or a force particle. But until you detect one, it's a virtual particle. If you detect one, then it's a real particle. But these are all pretty much allowed in particle physics, very, very much allowed in quantum mechanics and particle physics. So why not basically theorize something to do with quantum mechanics with a black hole? Because a black hole could benefit from such a treatment. So the whole thermodynamics thing for a black hole can actually make some sense if you did give it a quantum mechanical treatment and thought about the uncertainty principle. So it's clever. It's like making things up within a reason, though. In fact, it's making things up within the uncertainty principle, which is a part of physics, which is inherent to nature. So you can. It's not because you just feel like it. You can do that. It's allowed. So quantum fluctuations are allowed. However, they're the virtual particles, their indirect effects, just small changes in the energy of electron orbits in atoms, can be measured and agree with the theoretical predictions to a remarkable degree of accuracy. So even if you suggested, hi, bat shite, crazy, hello, and hello, John Foster. And I know there was a couple of questions. I'll go back up and read them in a bit here. So these particles, so once again, let me read this part again because I feel like I lost it a little bit. These particles are virtual. The quantum fluctuation, the annihilation, all that. These particles are virtual particles, like the particles that carry the gravitational force of the sun. Unlike real particles, they cannot be observed directly with a particle detector. However, their indirect effects, such as small changes in the energy of electron orbits in atoms, can be measured and agree with the theoretical predictions to a remarkable degree of accuracy. So that's good. The uncertainty principle also predicts that there will be similar virtual pairs of matter particles, such as electrons or quarks. In this case, however, one member of the pair will be a particle and the other an antiparticle or antiparticle. The antiparticles of light and gravity are the same as the particles. In the case of the electron, as you know, it's the positron is the antiparticle. It has the opposite charge. Because energy cannot be created out of nothing, one of the partners in a particle-antiparticle pair will have positive energy and the other partner negative energy. So maybe it's kind of like a couple. One of them is a particle, the other is an antiparticle. One of them positive, one of them negative. I hope not, actually, for the sake of people. I think both being positive is a good thing when it comes to the human beings. But in the case of the particles, the particle-antiparticle pairs are who are sort of the partners. The one with negative charge is condemned to be a short-lived virtual particle because real particles always have positive energy in normal situations. It must therefore seek out its partner and annihilate with it. However, a real particle close to a massive body has less energy than if it were far away, because it would take energy to lift it far away against the gravitational attraction of the body. Right? Thank you so much for liking the live. Can we get 20 likes? Normally, the energy of the particle is still positive, but the gravitational field inside a black hole is so strong that even a real particle can have negative energy there. It is therefore possible, if a black hole is present, for the virtual particle with negative energy to fall into the black hole and become a real particle or antiparticle. In this case, it no longer has to annihilate with its partner. Its forsaken partner may fall into the black hole as well. Or, having positive energy, it might also escape from the vicinity of the black hole as a real particle or antiparticle. I'm going to show you the picture for all this in just a bit. To an observer at a distance, it will appear to have been emitted from the black hole. So even though the quantum fluctuations and the particle-antiparticle thingy things could cancel each other out, sometimes maybe they don't, probabilistically. Sometimes, and within the uncertainty limit, of course, this shenanigan would not be happening, like there's an uncertainty limit that tells you sort of how much this can happen. But sometimes, maybe, basically the particle-antiparticle annihilation maybe doesn't happen. One of them falls in and one of them is emitted out. So to an observer at a distance, it will appear to have been emitted from the black hole if it does not annihilate with its partner and manages to sort of escape. The smaller the black hole, the shorter the distance the particle with negative energy will have to go before it becomes a real particle. And thus, the greater the rate of emission and the apparent temperature of the black hole. So again, this now it kind of makes sense that the temperature is more for smaller black holes, because the smaller the black hole, the shorter the distance the particle with negative energy will have to go before it becomes a real particle, and thus the greater the rate of emission. So if you're gonna escape instead of annihilate with your partner, it's better if you're trying to escape from a smaller black hole, right? And so those are the particles that are being emitted from, as observed by somebody else from outside, and that leads to having a temperature for that black hole. Because if you have a temperature, you must emit something. You must have a black body radiation, some kind of something, some thermal radiation. But because things escaping black holes was not really something we are super familiar with or really understand, This is why Stephen Hawking is doing all this work and coming up with the quantum fluctuations and particle-antiparticle partnerships and annihilation mistakes, or not mistakes, but misses because of the because of the uncertainty principle, for the thing to emit something, for the black hole to emit a particle or multiple particles. The positive energy of the outgoing radiation would be balanced by a flow of negative energy particles into the black hole. So this is another thing as well, which is that there is always that antiparticle. If you're talking about those quantum fluctuations happening, it's particle antiparticle. So there's also the antiparticle who may become a particle, who knows, who's going into the into the black hole. So the positive energy of the outgoing radiation would be balanced by a flow of negative energy particles into the black hole by Einstein's equation E equals mc squared, where E is energy, m is mass, and c is the speed of light. Energy is proportional to mass. A flow of negative energy into the black hole therefore reduces its mass. So now negative energy is going into the black hole, thank goodness, reducing its mass. As the black hole loses mass, the area of its event horizon gets smaller. But this decrease in the entropy of the black hole is more than compensated for by the entropy of the emitted radiation. So the second law is never violated. So this is how, this is where Birkenstein might not have expected this particular result, but that's what they're getting. So as the black hole loses mass, the area of its event horizon gets smaller, but this decrease in the entropy of the black hole is more than compensated for by the entropy of the emitted radiation because of that other particle, the partner who escaped. So the second law is never violated. Moreover, the lower the mass of the black hole, the higher its temperature. So we get that now. The lower the mass, more possible for something to be emitted. I think the temperature would just be lower for bigger black holes, for more massive black holes, but there would still be a temperature, probably. I'm just guessing. I'm guessing even the supermassive black holes have a temperature, but it's lower than for a less massive black hole, right? But we'll see. We'll see what he says. This is his thesis, not mine. I do believe that Stephen Hawking worked on this for his PhD thesis. He almost did not get a PhD because he thought he had that condition which would kill him, but then he kept living, and he also wanted to get married, and because of the wanting to get married, he wanted to get a job, and for that he needed a PhD, and that's why all this black hole stuff is happening. So he worked on this for his thesis, not me, for my thesis, and so he's the one who's going to tell us about all this. Thank you so much for being here. Can we get 20 likes? Can we? I worked on neutrinos for my thesis. He stuck around long enough. I worked on neutrinos, and so I know not what this guy is saying. I mean, I do know what he's saying, but him explaining it is far better than me trying to explain it. Long enough to get pally with. Well, I was going to say long enough to have a second marriage, I believe. So this girl, if I'm not mistaken, the girl he married, for whom he needed to have the PhD, is his first wife. He had a second wife, correct? Can somebody find out and put that in the chat? He stuck around long enough. Aw. But yeah, this is what he did for his thesis, I do believe. And so young Stephen will tell us about the black holes more. Thank you so much for listening, though, and being here with your discussion and questions. I worked on Conflict resolution. Ooh, is that a psychology topic? What's the field? Is that psychology? Tell us, Varun Malik, and thank you for being here. So, what happens when the mass of the black hole eventually becomes extremely small is not quite clear, but the most reasonable guess is that it would disappear completely in a tremendous final burst of emission, equivalent to the explosion of millions of hydrogen bombs. Ooh, human resource management. Ah, I see. Very cool. So, because the temperature actually increases, I did not know that he went to that island. Indeed, this is news to me that Stephen Hawking went to Epstein's Island. I mean, where from are you getting this news, Wonder Boy? Where from is the source of this? Because how small would that black hole have to be for that to happen? Isn't there evidence of ones smaller than the ballpoint on a pen? Ah, very nice. So I believe we're about to talk about small ones in a minute here. There was memes about it. The memes are the source? Goodness. He definitely. Oh my gosh. So you don't believe in the moon landing, but you believe that Stephen Hawking went to Epstein's Island because of memes? Are you for real? Are you serious? Goodness. The guy worked on black holes. Give him a break. Oh, it was confirmed? Oh, the game denied invite. Who's the game? See, I don't know anything about anything. I just read about black holes. I didn't know anything about such spicy news. And I still don't fully understand what's this island about. I don't think I get it. Is it illegal? He worked on some kind of... Wonder Boy. John Foster and Reese. Behave. Okay. What happens when the mass of the black hole eventually becomes extremely small is not quite clear, but the most reasonable guess is that it would disappear completely in a tremendous final burst of emission equivalent to the explosion of millions of hydrogen bombs. A black hole with a mass a few times that of the sun would have a temperature of only 1/10 millionth of a degree above absolute zero. This is much less than the temperature of the microwave radiation that fills the universe, about 2.7 degrees about absolute zero. So we know that the cosmic microwave background radiation is around 2.7 kelvins. So this situation of a black hole with a mass a few times that of the sun having a temperature of only 1/10 millionth of a degree above absolute zero is quite a tiny temperature, quite a tiny temperature, especially compared to, of course, the cosmic microwave background radiation, which has a temperature of around 2.7 kelvins. So quite a bit above 0 kelvins, right? Not a 1/10 millionth and whatnot. So such black holes would emit even less than they absorb. If the universe is destined to go on expanding forever, the temperature of the microwave radiation will eventually decrease to less than that of such a black hole. It hasn't yet, which will then begin to lose mass. But even then, its temperature would be so low that it would take about many million is here, one with 66 zeros after it, to evaporate completely. Kevin Hart's Who is that? You guys know more than me. This is much longer than the age of the universe, which is only about 10 or 20,000 million years. One or two with 10 zeros after it. On the other hand, as mentioned in chapter 6, there might be primordial black holes with a very much smaller mass than were made by the collapse of irregularities in the very early stages of the universe. So, with a very much smaller mass than that were made by the collapse of irregularities in the very early stages of the universe. So we haven't talked too much about primordial black holes. You've been living in a bubble. That's very true. I like to live under a rock and I don't know anything about anything. You're correct. I don't like knowing things. I don't know any islands. I don't know any Epsteins. I only know Einstein and Schwarzschild and those people. I don't know about their hobbies. Well, Einstein played the violin and I like that. But otherwise, I live under a rock. Under a rock and reading books. That's it. No islands for me. Other than the ones that are for snorkeling. To see little fishy. Pretty fishy is all I want to see. Sometimes. Every couple years. You know, important scientific fact that if deep impact happened in real life, I'll definitely be on the live. Deep impact? What do you mean? Okay. Thank you for liking the live. Can we get 20 likes? So these primordial black holes that we now speak of, that we haven't mentioned too much. That's not true. How do you know that? Excusez-moi. Okay. So we haven't really talked too much about primordial black holes. We just kind of mentioned it here. Oh gosh, that's why Newton is the GOAT. That's true. Poor Newton, so alone, so isolated, doing everything by himself, and his doggy, Diamond. I believe in the guy. So a primordial black hole with an initial mass of 1,000 million tons would have a lifetime roughly equal to the age of the universe. Primordial black holes with initial masses less than this figure would already have completely evaporated. But those with slightly greater masses would still be emitting radiation in the form of X-rays and gamma rays. These X-rays and gamma rays are like waves of light, but with a much shorter wavelength. Such holes hardly deserve the epithet black. They really are white hot and are emitting energy at a rate about 10,000 megawatts. So we will talk more about primordial black holes in a little bit. Maybe this is what people meant when they were asking me about the white hole. I hadn't really... Oh, Mike D? Sit down. Sit your behind down. Mike D, good thing you were timed out. Good thing. Oh, Wolfgang Pauli exclusion principle? I don't know what's happening anymore. Can we get 20 likes? Mike D, please do like the live right now. Do it. That's true. Newton was so innocent and amazing. Yes. Why not? Least he can do to redeem himself is like the live. Thank you, Mike D. Thank you, everybody. It's true. He was a ladies' hater. Aw, poor guy. So the next part of this chapter, he talks about primordial black holes. I think that is quite a bit to absorb. Like the live on your way out, D. No, I mean, Mike D can stay on. He just has to behave and not be timed out. That's about it. Oh my god. Varun. Like, please do like the live. Thank you so much. Is that why I haven't done anything as epic? The women. Maybe. I don't know. Maybe. 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 It's possible. Ah. Who has not understood? Oh. No one ever extended Newton's telescope. Poor guy. Anyways, I'm looking to see. Wait, do I have that one? Give me 1 second. Do I have that one? Ah. How small would that black hole have to be for that to happen? Isn't there evidence of one smaller than the ballpoint? I see. Primordial black holes. I think we will continue the primordial black holes next time. There was another question. Where is that? Oh, yeah. You asked about the supermassive black hole emitting radiation. And I said, well, it still probably has a temperature just lower than the... I feel another water break coming on, guys. Oh my gosh, you're correct. We should do an Epstein special. Well, let me know. What do you guys want to know about Epstein? Hello, El Challen. And I will be back. See you soon. I have to use the bathroom. I'm sorry, but I do have to use the bathroom. I'm here. YouTube is mental. What about YouTube is mental? One year? Something beginning with C? What do you mean? Did you see Baji moving? Oh! Did Baji move? There you go. You had the kitty cat here. Click on the smile face. You said that I won't be back? So you guys really like Epstein, huh? I'm catching up with your comments. Sorry. Sorry. She's actually returning. I am. I'm here. Do you see me? El Challen, hello. Top. Look at Baji's arm. Look at Baji's arm. He was entertaining you. I didn't leave you alone. All right. What? Who is strapping himself to what? Cool, just scrolling around the neighborhood. Temporary back up. Hello. Black holes, intergalactic portals, time travel, aliens, the usual. So somebody asked about wormholes. I think it was Steven who asked about wormholes. I might do a wormhole live. We did talk about it a little bit from this book though. That guy who wears the white suit with loads of people names written on it. Yeah, I was there. $5,000 card readers and 10,000 ASMR. What do you have against ASMR? I've got to go to a posh restaurant on Saturday. Are you going to miss the live? I was drinking Pepsi earlier, dreading it, to be honest. TBF, to be what? Double date thing with my brother and his stuck-up girlfriend. We're going to tell your brother that you called his girlfriend a stuck-up person. Goodness. ASMR is the epitome of the downfall of society. How long can tardigrass survive in space? I don't know what that means. What is tardigrass? What do you mean? I'm sorry. I'm sorry I missed you guys. That's too bad. The nail literally got stuck on my finger. What nail? I mean, she's alright, I suppose. She's just not one of us. They're like bacteria. Okay. So, the black hole stuff was interesting. I can't believe that, I mean, I can, but I'm still settling down with the fact that the bigger ones have lower temperatures. It makes sense though. It makes sense though. I will say it does make sense. It makes sense. And I will keep in mind that somebody asked about wormholes and somebody asked about nova. I just couldn't talk about nova today in a lot of detail, and I couldn't talk about wormholes today in a lot of detail. I am sorry. I will talk about that next time. I was welding a nail to fill in a gap. His girlfriend and tardigrade are both bacteria. Got it. It's a microscopic animal that Neil deGrasse Tyson talking about that can survive extreme heat and live in space for a certain amount of time. Oh, I see. Neil deGrasse. I do say. Where was Doro today? Did we see him? Did we see him? How is everybody? How are you, John? John Foster, Reese. Shall we read a little bit more about primordial black holes, or you guys want to chit-chat? She's nice, but she has him whipped. I shouldn't have read that. I did that automatically. Watching Craven, it's horrible. Why are you watching it then? Why are you watching it? So there might be primordial black holes with a very much smaller mass. Oh shoot, you know what? I have low battery. I still got a few minutes though. No, like I will show a figure at the end of the live. I will put it to charge over there and show you guys this figure that I had in mind. Like, he's under the thumb. Yeah, no, I know what you mean. I know what you mean. A figure, yeah, a diagram. Right? A diagram, a plot, a picture. I will be showing a picture at the end of this live to explain something. Hang on. Where did Varun go? Varun had some interesting things to say. Where is he now? And did you guys talk further about Epstein? What did I miss? What was the summary? Give me the summary. What did I miss? As mentioned in, there might be primordial black holes with a very much smaller mass that were made by the collapse of irregularities in the very early stages of the universe. Such black holes would have a much higher temperature and would be emitting radiation at a much greater rate. A primordial black hole with an initial mass of 1,000 million tons would have a lifetime roughly equal to the age of the universe. Primordial Indeed, it is not. Indeed, it is not a picture of Hawking on the island. I didn't even know that he went to the island. That is you thinking that he did and saying that he did. Indeed, I'm not sure that that is true or not. Indeed, I only read from the book and understand black holes. Random question. What do you usually eat for breakfast? I ate Lucky Charms cereal today. Doing donuts in the sand in his wheelchair. Oh, aw, that's kind of nice. Doing donuts in the sand with his wheelchair. Let him have fun. Gosh. Gosh, oh gosh. I had cereal today and coffee. Then I had Nepali thali for dinner, lunch come dinner. Then I did swimming. Why? What did you eat for breakfast? I thought that cereal was discontinued. Discontinued where? As in cereal is not eaten anymore by people? Think he's had enough. Oh! I don't like this suggestion. Swimming nice, are you a good swimmer? I don't know. I just swim a lot. I don't know if I'm good or not, but I just do it. Just do it. Just do it. Oh, Lucky Charms. Daisy, hello. Hello. Lucky Charms. It's a thing. I ate it today from Walmart. Lucky Charms is still available in the Walmart. You dog paddle? I don't know what that is. Like a doggy swimming in the pool. I just swim freestyle. Like where you move your arms and legs to move forward and then do it again and again and again. I just swim laps. I mean, you might not like it, but it's true. Okay, Wonder Boy. Hello, Daisy. What's up? How are you, Daisy? Anything you want to say in the chat? Just like the fact that all the astronauts are... I don't know what that means. So you have a pool. It's a style of swimming. Okie dokie. I go to the gym. The gym with the lap pool for swimming is how I swim. Freemasons? Oh, cool. Yay. Yay for what? Yeah, so I go to the gym. I need a very specific pool with a very certain depth. All the way across should be about that same depth. And I keep swimming lap after lap in that pool. So that's how I accomplish my swimming. 8 feet? No. More like 5 feet. I don't want to be in a depth where I can't stand. If I'm swimming as a workout for my, mental health, gym swimming, which is what I do, I want it to be around 5 feet all the way. Not, how tall are you? I'm not 8 feet. How tall do you think? I'm not 8 feet tall. So it needs to be 5 feet-ish. It could be a little more, a little less through the whole length of it. And I should be able to stand at any moment. Who do you think is 5'3"? Are you calling me short? I'm taller than that. I'm taller than that. So, so, I just need to be able to swim the laps. This way, this way, this way, this way, this way, this way, this way. Constantly laps, constant laps. 5'6". I mean, I'm not a model. Well, I guess I could be. I'm kind of a model, right? Sort of. but, 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 the thing has to be a depth that I can stand and not drown. There's nothing wrong with that height, lol. There's nothing wrong with any of these heights. I'm just giving you a hard time. So all these heights are good. All the heights are good. So anyways, yeah. I wanted to be 6 feet when I was young. Like a really tall tennis player. I wanted to be... Noticed what? What'd you notice? I wanted to be 6 feet tall. I wanted to be 6 feet tall, but I'm not. But even if I was 6 feet tall, I would still be 2 feet less than 8 feet. So no, I don't want the pool to be 8 feet. No. I'm extremely afraid of deep water. Unless it's the Caribbean Sea and it's warm and very salty and you can just kind of float. And I'm on vacation. So then it's fine. But otherwise, with the pool, it needs to be the same-ish depth throughout of about 5 feet maybe. Really less than 5 feet probably, you know. Yeah. So the pool is extremely important. The depth of it, very important. Wonder Boy, nobody asked you. Nobody asked you about tall women. Nobody. Okay? Police. Also, tall is so subjective. I'm tall. I'm taller than somebody who's 4 feet. Subjective things being said. Don't say anything against my tall girlies. I'm a short girl. I'm a short girly who's for the tall girlies and short and all the girlies. I'm a girlies girl. I got hit on. Okay. Oh my god. Are you calling me short? Oh my god. I am not tall or short. I will have you know, I'm average. It's not short or tall. I am the exact average height of women in America. Exact average. A hair taller than the exact average height of women in America. So I'm not short. Excusez-moi. Excuse you. You are short. Or tall. Whichever one is negative. Actually, both are great. Both are fine. Both are great. Be short. Be tall. Both are great. Thank you. Thank you so much. Can you please like the live? Can we get 30 likes? 5'7"? Do you wear heels? No. They hurt. Average height, above average water break durations. 5'7". 5'7" is not the average height. What do you mean? I'm gonna Google it. Hey Google, what is the average height of women in America?
On the website health.com, they say the average height for women in the U.S. is 5 feet 3.5 inches. Genetics initially determine your height potential.
5.35. Best thing I heard from a woman? What do you mean? Which best thing? 5'7" is not short. Excuse me. 5.35 is the average height of women in America. So that's not short. That's average. And I'm a little taller than that. So I'm really tall. You're tall. Yes, I'm tall. You don't wear heels because they hurt your feet. Yes, of course. Yeah, heels are bad. I have some pairs of heels, but are you serious? 5 feet 3.5 is the average. God, you know what? I mean, I think you guys don't understand what the definition is. Definition. I'm 4'9". See? Thank you, El Challen. But you're a kid, right? El Challen is 4'9". I'm taller than that. Excuse me. I am 5 feet 4. Oh my God. No. Oh my God. A booster seat. Oh my God. What the frick? You guys don't know. You guys don't know that the average height is 5'4", or no, 5.3. Oh my God. Oh my God. Oh, this is unbelievable. You guys don't know what short is. 5 feet, 5.35 is average. So you have to be shorter than that to be short, and taller than that to be tall. So since I'm taller than that, I am tall. Oh my God. What is this nonsense? Your water bottles look, oh my God, this is unbelievable. I can't believe it. That's obviously the camera angle. This is all camera angle. The phone is right here. This is a 16.9 fluid ounces. Okay? 500 ml for the British people or whoever. This is the camera. I can sleep on a twin size bed. Yeah. So I have a queen, but I can sleep on a twin. This is so skewed. I can't believe you guys think that 5 feet 4 is short. That is tall. It's a little taller than average. How much is an inch? Is this an inch? I am this much taller than average. Wait. Is this an inch? This you guys have no. I'm just shocked. I'm shocked. Oh my God. Now I have to blow my nose. I can't believe it. You guys think that 5 feet 4 is short. That is not short. Yeah, it's true. I have to take a lot more steps to cover the same distance as somebody taller. It's relative. You know, tall and short is all relative. Relative to the average height of women in America, I am this much more tall, actually. This much. But I do like this comment. Sometimes she falls on the cat's foot. This is why the water is. But I will say that you're wrong about the tall short thing. Do you or do you not have multiple? How do you know that? Step stools? Yes, I do have step stools. One in each room. Why? Why? I thought everyone has that. Don't you? JG2 goated. I thought everybody has. Actually, today I was on a step stool to open a vent. This girl right here, opened a vent. What's your age? It's not a kid age, if that's what you're asking. I don't go to Walmart. I get things delivered. I went to Home Depot a couple times and everything is too up there. So I don't go to Home Depot anymore. And I don't go to Walmart. Screw that. You have to take the stools with you to Walmart. No, because I get it delivered. But today, do you stay indoors a lot? Kind of, yeah. When I go outside, I take walks. I go to the gym. I go outside. I take walks. I explore Boston. I do struggle with driving. So I have to take the train a lot and the bus. One time, this bus driver told me, get out. Now, I didn't have enough money on my Charlie card, but I thought he was rude. Very rude. There have been a number of times when they let me ride it for free. But this one time, she just sits there. I can't believe it. You guys think that 5'4" is short. Wow. That is not short. That is the over average height. Over average. Anybody taller than that is basically a giant. How's the weather? Up there. Your body is doing a lot of work, circulating all that blood everywhere. How did this happen? First of all, you guys were talking about Epstein, who I think is pretty controversial. Then somebody said something bad about tall women, and that's what got this started. I think it was you, Reese. I blame you. Why did you have to slander tall women? Whatever that means. What am I looking at? Oh, here it is. John is 5 feet flat for sure. Okay, whatever. Let him be 5 feet. Are you visible? I'm clearly very hugely visible. JG. John. Oh my God, this JG. John is 5 feet flat for sure. 6 feet, 5 feet, 6 feet, same thing. Same thing. Who cares? Who cares? I only care about my height, which I wanted to be 6 feet when I was young. I for real thought, when I was like around 10, 11, I thought I would grow more and get to 6 feet tall and play tennis because I liked tennis, among other things. Yeah, I wanted to be like Maria Sharapova. Isn't she like over 6 feet tall? Google her. So I thought, oh my gosh, to be like a tennis player doing those amazing serves, you had to be tall and like run faster and get to the ball faster. And I was like kind of struggling. So I was like, dear God, please make me 6 feet tall. And I thought I would at least be 5'6". I thought I'd at least be 5'6". At least. My grandma was like 5'8". So I'm not sure why I became 5 feet, 5'4". It's a little shorter than I was. I noticed most sports are tall people dominated. Yes, honey, it is. Life is a box of chocolates. When did you realize you weren't going to be over 5'4"? You know what? Maybe I'll still become 6. I don't know. I was hoping and hoping that I'll someday become 6 feet because I'm very optimistic. As a person, I'm very ambitious and optimistic. So I started to think that if I just will myself, I even hung. I even hung from a rod. To make myself taller. I even hung. Hung as in? Yeah. Not hanged. Hung. To make myself taller. I was hoping that my arms would just like, you know. She tried to stretch herself. Yes! I did. Do you guys not do that? Do you not do that? Do you guys not try to stretch yourselves when you're young? I did that. I tried to stretch myself. Go like this. Hang from a bar. That's how Epstein went down. He got hung. That would be hanged, not hung. Right? Do you even know English? So I even hung. I stretched me. And I thought like, definitely my legs are going to be more stretchy, or my arms will go stretchy and my entire torso will become more stretchy, right? I thought. We're all over 5'10". What? Oh, I'm just kidding, John Foster. Don't worry about it. Hung, hanged, who cares? We're all over 5'10", so I'm going to say no to stretching ourselves to get taller. You didn't? you didn't stretch yourself? How did you get taller then? I thought more stretching means more tall. See, I wanted to have some level of, I wanted to decide how tall I would be. So I figured, well, I know at least one woman in my family who was pretty tall, 5'7", 5'8". I think my grandma. One of my grandmothers was like 5'7" or 5'8". Now my other grandma was more like really short, like 4 feet something. And my mom is like a little shorter than me. So I thought I'll have some say in how tall I can be. I was optimistic. I was optimistic. I want to be 6'4". Yes, I wanted to be 6 feet. I thought I'll get there. I was already 5'4" by the time I'm like 11 or 12. So why not? I thought I can keep growing till I'm 21 or something, right? Little did I know that I would never be any taller. I've been the same height since I was like 12. Or maybe 13. I don't know. Or 14, I don't know. My other grandma was like 4 feet. Actually, yeah, she was like 4 feet. Do you think it's because of that? My one grandma was 5'7", and the other one was 4